In this lesson, we're looking at absolute value equations and inequalities. First up are the equations. The definition of an absolute value is the distance between the number and 0 on our number line. So if we have our number line and we look at, for example, the number 3, then the distance to get from 0 to 3 on the number line is 3. So we say the absolute value of 3 is 3. Similarly, if I wanted to get to -3, 1, 2, 3 spots away from 0, that distance is also 3. And that's why the absolute value of -3 is equal to 3. Looking at 0, the absolute value of 0 is 0 because we're already there. The distance is 0. Now let's take a look at some properties of absolute values. The absolute value of a number is always greater than or equal to 0. Distance is always positive. So we maintain that distance definition when we talk about absolute values. Also, the absolute value of one number and its opposite will be equal, as we saw with 3 and -3. We have the same distance away from the number line. Similarly, if we start throwing operations in there, the absolute value of a minus b is going to be equal to the absolute value of b minus a. To give you a solid example for this one, if we had 3 minus 1 in absolute values, and we switch them, 1 minus 3, 3 minus 1 would be 2, 1 minus 3 would be -2, and we have that same relationship as we have in number 2. The absolute value of 2 equals the absolute value of -2. So if we switch the order in the subtraction, we're really just changing the sign on the answer. Also, one more thing to point out, if I have the equation, absolute value of x equals 3, for example, then what is x? Well, we've already found the absolute value of 3 is 3, and the absolute value of -3 is 3. So x could be 3 or -3, as we saw above in the number line. So this absolute value, if we're trying to solve for x, absolute value of x equals k if and only if x is positive k or negative k. And this works for any positive real number, k. So here, k is 3. Try this again. If we asked, what is x if the absolute value of x equals 5? X would have to be 5 or -5. So we get the positive and the negative of that number. Okay, well, what does that mean in the context of equations like we have here? Well, what we're going to do to solve these absolute value equations, I'll walk through number 1 with you, and then we'll do some more as we go as well. So in the first one, the absolute value of 3x minus 2 equals 7. Now, above in our explanation, we just had x in the absolute values, but this time we have more than just x. All that means is we're going to copy that piece over and just change the sign. So here we have 3x minus 2 in the absolute values. So we'll create two equations. 3x minus 2 equals 7, the positive k, and 3x minus 2 equals -7. So we're changing the sign in the second equation. Creating these two equations, notice that we have 3x minus 2 repeating in these two equations. That's intentional, it's on purpose, and it's exactly what the line above is really referring to. Now, solve each of these equations for x. We would do them separately, pretty much like we were doing those compound inequalities with or. We solved each one separately and then put them together at the end. So here, 3x minus 2 equals 7. We would add 2. 3x equals 9. So divide by 3. And x equals 3. So we have one possible answer that would solve this absolute value equation. And now we focus on the second equation that we created by changing the sign, -7. So same steps, get x by itself. We'll add 2 to both sides. So 3x equals -7 plus 2 will give me -5. Divide by 3, and we get x equals -5/3. So here are our two answers. If we graph them on a number line, it's not terribly exciting to graph equation answers on a number line, but 1, 2, 3, somewhere over here, and then -5/3, it's a little bit closer to -2 than it is to -1. And so we have two answers, -5/3 and 3. And if we were to take these numbers one at a time and plug them back into this equation up here, we would get the absolute value equaling 7 for both of those numbers. So notice what I did. The absolute value equals a number. I turned it into two equations and dropped the absolute value part. We're going to do that same thing in number 2, but we've got one step that we need to do first. Can you see what it is? We cannot make a new equation until the absolute value part is by itself. So we need to isolate the absolute value part. This is analogous to us solving those radical equations where we had to get the radical by itself first and then we could square both sides. The same idea here. And you'll see this commonality throughout all of what we do in solving equations. We need to isolate the part that makes it that type of equation. We have an absolute value equation here. We need to isolate the absolute value. If it's a radical equation, we need to isolate the radical. Later on, when we talk about exponential functions, we'll need to isolate the exponential. So we'll see this idea of getting that thing by itself first and then proceeding through to solve it. So we need to get x plus 7 by itself first, the absolute value of x plus 7 by itself first. So let's subtract 2. Notice I'm not creating the two equations yet. I can't. I've got to get the absolute value by itself first. So subtract 2, and we get absolute value x plus 7 equals 10. Absolute value is by itself now. Now I can create my two equations. X plus 7 equals 10. X plus 7 equals -10. Absolute value gives us a positive answer and a negative answer because we're solving for what's inside the absolute value. So since the numbers inside, a positive number and a negative number inside the absolute value will give us the same positive answer, here to find x, we take the insides and set the insides one positive, one negative, and solve. So going through the motions, solve the first equation. Let's subtract 7. 10 minus 7 is 3. The second equation, let's subtract 7. -10 minus 7 is -17. And we have our two answers here. We can do the same thing like before with our number line. We've got a point at -17 and a point at 3. I could check my answers, and I'll do that here onto the side. I can check x equals 3. 3 plus 7 in the absolute values plus 2. Does that equal 12? 3 plus 7 is 10. Absolute value of 10 is 10. 10 plus 2 is indeed equal to 12. I could do the same thing with -17. -17 plus 7 plus 2. Does that equal 12? -17 plus 7 will give me -10. The absolute value of -10 is +10. And 10 plus 2 also equals 12. So both of our numbers work out. Try number 3 on your own. Pause the video. See if you can come up with your two solutions for number 3. And when you resume, I'll have the answer so you can check. And we get two answers here. X is 13/5 and x is -7/5. Graphing these on the number line, 2 points on the number line. Again, it's not that exciting, but it's good practice. 13/5 will be on the right, -7/5 somewhere on the left, 0 closer to -7/5. I'm not terribly picky with putting the tick marks inside the number line for the inequalities, the compound inequalities and the absolute value equations and inequalities. That's okay. The big idea is that when you're doing absolute value equations, you could have two answers. You could have one answer if the absolute value equaled 0. You get one answer for x, or you could have no answers. So I'm going to save number 4 for right now. I want you to look at number 5. What do you notice about number 5? Do you see it? Well, in number 5 here, I've got the absolute value equaling a negative number. absolute value is always positive, but here I have a negative number. There's not any situation where a positive number will equal a negative number, ever. This has no solution. There's no x value that I can put on the left side, use all of those operations, 7 times that number minus 1, then take the absolute value and expect to get an answer that's negative. Never going to happen. So we have a no solution situation. Notice above in the statement, any real number k is greater than 0. K has to be greater than 0. The number that the absolute value part equals has to be greater than 0 in order for us to have solutions. So that's why paying attention to that detail is really important when we're working with these equations. Looking at number 4 now, things are a little bit different. You can see that we have 2 absolute values here, and these 2 different absolute values, we could create 4 equations to solve, but it turns out that 2 of those equations are actually equivalent to the other 2 equations. So instead of having 4 equations, we really have 2. And here's what I mean by that. We have 2x plus 1 equals 4x minus 3. Just drop the absolute values. They're the same sign. Or the 2 sides are opposite in sign. Opposite in sign just means we have one negative sign on one side of the equation. So to create the 2 equations for a double absolute value equation like this one, the first equation, we drop all of the absolute values and write it as it is. The second equation, we'll copy the left side. On the right side, we'll include a negative sign on the whole thing. Remember, we want an opposite of whatever 2x plus 1 is. So opposite means negate all of it. And so the first equation is representing the same sign. Both sides are positive or both sides are negative. And the second equation is representing opposite sign. One side is positive, the other side is negative, but the negative on the other side is going to change the sign so that they're the same. And they're equal. Okay, so solve the 2 equations. Let's go through it. I want to get the x's on the same side and the numbers. We get 4 equals 2x, so we'll divide by 2. X equals 2 for the first equation. Second equation, we need to distribute that negative sign. Remember to distribute negative 4x, negative 3 becomes a positive 3, and I'm going to add 4x this time so that I keep my x's to be positive. And we'll subtract 1, 6x equals 2, so x equals 2/6, but we can reduce that fraction and it becomes 1/3. So we have x equals 2 or x equals 1/3. As our answers. In the next part of our lesson, we talk about absolute value inequalities, and we're going to bring back all of that stuff that we learned for compound inequalities in our absolute value inequalities.